Oh, okay. I'm not sure exactly what happened. Looks like we got disconnected. But you know what? I'm gonna just keep going. Hopefully, this isn't much of an issue, and it will resolve. Just had it. Yeah, I was just in the middle of listening to lecture 8 again. I'm trying to get a better grasp of how he did this solution for the quantum harmonic oscillator.
No unit. I has the same units of the atom. These signs have no unit because you cannot find the sign of 1 centimeter. So this thing, we should have the same thing here. No. So how can we do that? This is an absolutely necessary first step. You're going to be carrying all this to get nowhere. So we have to clean it up. So what I'm going to try to see is that, look, here is psi, psi, and psi. So suppose I do the following thing, that I will clean up the right-hand side by dividing by something with units of energy. So I'm going to do it the following way. I'm going to divide all by over h bar omega, and this 2, and I'm going to multiply by 2. So I'm sorry, not divide all by the by 2. What do I achieve with that first step? I achieve that these 2's disappear. Well, not that either, I think. But in the right-hand side, this has units of energy, and the right-hand side will not have units of energy. So what do we get here? So we get minus. The h becomes an h alone over the m disappears, so m omega. The second psi, the x squared. The 1/2 disappears, so m omega over h bar x squared psi equals 2e over h bar omega psi. Now it looks actually quite better already. Should agree with that. That looks a lot nicer. Now I can use a name for this. I want to call this the dimensionless value of the energy. So a calligraphic E. It has no units. It's telling me if I find some energy, that energy really is this number, this pure number is how many times bigger is E with respect to h omega over 2. So I'll write this now as E psi. And look what I have. I have no units here. And I have a psi. And I have a psi. But things have worked out already. Look, the same factor here, h over m omega, is upside down here. And this factor has units of length squared. Length squared times dd length squared has no units. And here is 1 over length squared. 1 over length squared times length squared. So things have worked out. And we can now simply say x is going to be equal to a u, a new variable. This is going to be your new variable for your differential equation, in which a is this thing, and then this differential equation, probably I'll go here, really has cleaned up perfectly well. Oops. So how does it look now? Well, is 1 over a squared, d squared. And this thing is a squared. So actually, cancel this factor. And when I write x equals to au, you get an a squared times this, and a squared times this is 1. So your differential equation has become the second psi the quantity, because this has units of length, no units here. No units. So minus the second u squared plus u squared psi is equal to e psi. Much nicer. This is an equation we can think about without being distracted by this endless amount of little trivialities. So, but still, you know, we haven't solved it, and how are we going to solve this equation? So think of what should happen. Somehow it should happen that this fixed solutions just for some values of e's. It's not obvious at this stage how that. Yes. Here, for example, let me do this. This h bar over m omega is minus from that equation a squared, but the 1 over a squared d. So the a squared cancels. And here a squared times u, so again cancels. Okay. So what is the problem here? The problem is that most likely what's going to go wrong is that this arbitrary values of e's is going to diverge. I'm never going to be able to normalize. Let's try to understand how the solution looks as we go to infinity. So this is the first we should do with an equation like that. How does the solution look as you goes to infinity, but we're going to gain. So it is what, when u goes to infinity, this term, is much bigger than that, because we're presumably working with some fixed energy that we still don't know what it is, but it's a fixed number, and for u sufficiently large, this is going to dominate. So we're trying to solve as u goes to infinity, the equation sort of becomes psi double prime, prime is for two derivatives, equal to u squared psi. Okay, so how do we get an idea of what solves this? It's not all that obvious. It's certainly not a power of u, because when you differentiate a power of u, you lower degree rather than increase the degree. So what function increases degree as you differentiate a function cannot be a polynomial. If it were even a polynomial, this cannot be equal to x squared times a polynomial. It's sort of upside down. if you think about it for a little while, you don't have an exact solution, but you would imagine something like this with an e squared. Because an e to the u squared, when you differentiate with respect to u, you go down. When you take another complicated, but one term, you will use another u down. So that probably is quite good. So let's try that to see if we have something like
Okay. So I think this is the thing that I was messing up. D.
So I will try something. I'll try to over 2, where alpha is some number. This, I actually want to emphasize to you, if this is the behavior near infinity, difference if here, for example, something like u to the power k, so be roughly a solution. So let's see that to differentiate. Let's see, trying to see how the function behaves far, far away. Look, alpha should be negative, but let's see what the function tells us before anything in there. So if you do psi, you will get what? You will get one term that will be out this u to the k.
Yeah, so stream isn't that great, guys. I quality is getting a little lower right now.
If you take a second derivative, well, I can define exponential again, so I will get now squared. Because each term so you get k, u to the k minus the second derivative.